So let's start with something that well, people here should be very well familiar with graph homomorphisms. So if I want to state the k-coloring problem, it's of course the question, right? Well, can I map my given graph to this pentagon so that every edge is mapped to different, every vertex, every edge is mapped to an edge here? Well, which basically means that this has to be a homomorphism. So every k-coloring is a homomorphism to kk. Well, in the decision version of the problem, we just need to decide if such a thing exists. If in the counting version, we have to count how many proper colorings or how many homomorphisms we have here. Well, it's easy to generalize to H coloring, right? So if we replace the complete graph with just arbitrary graph, say let's call it H, then what we obtain, again, it's about counting homomorphisms now to the graph H. We obtain the counting H coloring problem. So that's what was the subject of research, well, in particular by Pavel, who is one of the founding figures of, I believe, of our department for sure. So if we care about the complexity of H coloring, of counting H coloring, well, let's say it's completely known. So let's see when we can count homomorphisms to a graph H and when we cannot. The answer is basically we almost never can, except for really trivial cases. Well, it's a hard problem, and the trivial cases are, well, I will assume that H is a connected graph. It's just if it's disconnected, it makes no sense. I mean, you can reduce to connected case easily. So if H is a complete graph with all loops, so if you think about that, right, you have everything connected and loops. So any mapping will just give you a homomorphism, or a complete bipartite graph. Again, if you have a bipartite graph and you want to map find a homomorphism, to get a homomorphism from a graph to a bipartite graph, your given graph should be better bipartite as well. If it is bipartite, well, anywhere you map, is a homomorphism to a complete bipartite graph. If it's not, okay, well, there is no homomorphism at all. So in this case, it's kind of the easy part is really easy, but the hardest part is a little bit tricky. So in this case, you need to work a little bit and come up with a bunch of reductions and stuff like that. So if we talk a little bit more about this little example and ask questions, for instance, what does it mean that it's hard? Well, we can think that, okay, hard in any reasonable way, say it is NP hard, for instance. But if we want to be correct, then the hardness here means sharp P completeness. So sharp P is a very well-studied complexity class. It is the class of functions that work as follows. You take a problem from the class NP, like k-coloring, for instance, right? It belongs to NP because there is the non-deterministic Turing machine that accepts or rejects or whatever. And your problem is to count the number of accepting paths in the computation of such a machine. So for instance, if you have k-coloring, right, every accepting path may correspond to a coloring, and then you count. So that's the idea. So hard means hard for sharp P. It's a huge class. It's almost as large as P space. It's big. So this problem is really, really hard. And also, if we mention a little bit about, well, how we reduce problems, since we're talking about completeness, for instance, it's usually understood in the polynomial time. Say I can solve problem A. I say that problem B is reducible to that one. If I can solve B and ask about some solution to A from time to time. So if I use A as an oracle, this is the proper term. Well, there are other concepts of reductions, but well, we kind of allow ourselves as general one as possible. Okay, so that's basically the pre-CSP situation in this case. So that's what is known, and so on. Okay, so let's try to make the model a little bit richer. And what we can do is first of all to replace graphs with something more complicated. And by more complicated, well, I will mean relational structures. Again, so what is relational structure? Well, I wrote a formal definition here, but in a nutshell, you have a set and bunch of relations on this set, right? If you have a graph, you have just one binary relation, right? If you have something more general, okay, well, you have more relations, maybe higher arity, whatever, right? So graphs is just, or digraphs is just a relational structure with one binary predicate, so sort of simple case, and well, you can add whatever you want. Then you are getting relational structure. So that's the idea behind relational structure. And again, I was told that we have a connectivity problem here. Okay, a couple of examples. So digraph is a relational structure with one binary predicate. Let's look at a just two-element set, 0, 1. I introduce, it should be ternary relations. I will introduce ternary relations that are expressible by three clauses. So for instance, all assignments to x, y, z that satisfy the clause. So I would have, well, there are 8 possible assignments, 7 of them are satisfiable. So every such relation would include 7 assignments, but leave out 1. So 8 possible assignments, 8 possible relations. So in this case, okay, well, I will say that this is some relational structure H3 such, and well, I will say why H3 such in a minute. Or for instance, we can take some finite fields and consider relational structure again with the base set on the set of elements, which is just the elements of the field, whose relations are expressible by linear equations with coefficients in the from the field. So if we think of in terms of linear algebra, those will be hyperplanes, right? Such relations would be hyperplanes. So 3 here corresponds to, I wanted to say that linear equations must have exactly 3 variables in them. So the number of non-zero coefficients should be 3 or less. So in that sense, it's 3, and k, of course, corresponds to the size of the field. Okay. So once we have this relational structure, we can define what a constraint intersection problem is. We say that a relational, well, the instance of such a problem is again a relational structure of the same type, so having the same relations, right? The same signature, sorry, as H. And the question is, how many homomorphisms do we have from G to H? So if H is a graph, G should be a graph, right? And then we're asking, okay, how many homomorphisms are there from a graph to a graph? If we talk about kind of more general relational structures, again, we can define this concept of homomorphism in a very natural way. It maps every tuple from a relation here to the corresponding relation there. That's basically how it works. Okay, so this is the constraint satisfaction problem. H coloring only for relational structures, nothing else. Okay, so for instance, for H coloring, it's exactly CSP of H. Well, we can use this notation for relational structures if we want to. Okay, every time I touch it, it changes color. All right, so some examples. For instance, if I look again at that relational structure, if you remember, F3K, for instance, where relations are expressible by linear equations. So if we have just a 2-element set, and if I define all relations by, well, basically linear equations, or maybe systems of linear equations, doesn't matter. Then such a CSP can be solved in polynomial time, counting CSP. Well, this is what this result basically says. So let's see why this is true. Well, I have these relations, right? I have this, they are given by linear equations. So the whole CSP is about, well, I need to assign things somehow so that all equations are satisfied. So the whole problem is a system of linear equations. Now we have a finite field. Well, two element or greater than or bigger than that. I have a finite field. How do I solve a system of linear equations? Okay, well, I construct a basis. Right, so I have this basis. Now, what's the dimensionality of the solution? Well, I have some number k, for instance, for the dimensionality d for dimensionality. Then how many solutions do I have? Well, I can take, say, some basis vectors. Any linear combination will do. So the number of solutions would be the size of the field to the power of d. Right, so just from linear algebra, I can easily count how many solutions to a system of linear equations I have. That's really easy. And the surprising thing that is, in all other cases, it's hard. So far we have two reasons for a CSP to be easy, for counting CSP to be easy. One, it's trivial, which is a not particularly good reason, and another one that it's somehow a system of linear equations. So we will see one more reason for a CSP being easy. Okay, and that's the result I mentioned already. So for actual H coloring, the reason for easiness is just that the problem is trivial. Okay, what else? So, okay, other counting CSPs, say counting satisfiability. I have a CNF, I want to count the number of satisfying assignments. Well, if I want to restrict myself a little bit, well, I don't want to allow very long clauses, then I say, okay, let's count this 3 sets, right? Only clauses of size 3. In this case, what I get is exactly the CSP of this nice small relational structure H3 sets. And so what do? I have these relations expressible like clauses, right? And I need to find an assignment that makes all clauses satisfied. Right? That's exactly the CSP problem. So that's another example, and of course this one is hard. Well, that's no doubt. It's Sharpie complete. This one is Sharpie complete, of course. Well, and linear equations. Well, I basically mentioned that if we represent every, well, we can make it the same as the problem CSP of F3. Okay. So in terms of complexity, what kind of landscape do we have? Well, we have a bunch of problems, right, that we've seen so far. Some of them are hard, right? Some of them are easy. Some of them, well, it depends. So in this case, it's hard. Well, in this case, it's easy. In this case, it's hard. Some kind of a different relational structures, different problems, different complexity. So what I'd like to do, I would like to figure out what is the exact complexity for any possible relational structure. So it's done for graphs, for instance. How about more general relational structures? So this is the problem I am going to solve. Classification problem. Okay. So an interesting comment on such classification problems is that in the case of the CSP, one of the frequent shapes of results is something like this. I give you a special case of a CSP, right? Like, I don't know, for say H coloring for some specific graph or diagram. And in many cases, it always happens so that it is either easy or it's as hard as possible. And there is nothing in between. So for instance, here, there are a lot of complexity classes between polynomial time and Sharpie. But in all the examples we have seen so far, well, the actual problems don't attain any of the intermediate classes. So they're either at the very bottom, they're easy, well, sometimes trivial, or they're as hard as possible. Right? And then there is nothing in between. If this happens, we say that we have a dichotomy, a complexity dichotomy. Right? So either here or there, well, and there is nothing in between. So the hope is that a solution to that would be also such a dichotomy. It's either easy or as hard as possible, and nothing in between. And nothing in between. Okay, well, we will see that this exactly as it happens. So, well, as the first step towards that, let's try to check if we have any more reasons for counting CSP to be easy. And well, I will talk about rank, which is just matrix rank of a matrix, nothing really special. But we need to construct the matrices kind of carefully. Okay, a motivational example. So let's look at a couple of diagrams like this. Okay, so I'm going to look at the counting H column problem to here and to here. And as you may guess, one of them is going to be easy, the other one is going to be hard. So any bets which one is easy, which one is hard? There is a lot of stuff here, right? And that one is so nice. Okay, so what would be the right way to approach the problem? Let's see. So what I want to, well, the difference between them is, of course, the number of those intermediate vertices in this middle level, which are connected to some vertices on the top and on the bottom, right? So the vertices in the middle level that are connected to this and this one. Well, in this case, there are 2, and in this case, there are 4. So between these 2, I have 2 vertices. Between these 2, I have 1 vertex. So what is the idea? I will construct a matrix out of this example as follows. I say that suppose the rows of my matrix correspond to vertices on the top. Right? The columns of the matrix correspond to vertices on the bottom. And the entries will be, well, how many vertices I have between them. Right? So for instance, first row, first column, I will have 2. In the first row, first column, I will have an entry 2. So if you look carefully, well, the matrix here would be something like that. It's 2 vertices between these 2, and 1 between everything else. So this one corresponds to the 2. Then the 2 corresponds to these 2 vertices and 2 vertices between them. This one would be what? It would be the first row and second column. So 1. This one is here, and this one is here. So for this matrix, we will have 4, 2, 2, 4, or 1, sorry. 4, 2, 2, and 1, something like that. Okay, any observations about these 2 matrices? Why one of them is better than the other? Yeah, so one has low rank, right? So the second matrix has rank 1, obviously, and the first one has rank 2. So that's exactly the difference that is responsible for the complexity. So let's try to do the computation. So why say, well, I want to show why this one is easy, how to solve that. Well, normally I would write this on a blackboard or something, the computation, but okay, I thought that maybe it's going to be technically not so easy, so I just put it on slides. So let's see how it works. Okay, that's our graph. I just numbered vertices 1, 2, 3, 4. That's it, nothing else. Well, I put the first one because it's kind of nicer, small, and so on. But actually, I will use the second. So that's just kind of to create some idea of what we have. So the matrix I'm going to use is this. So matrix doesn't agree with the picture. Sorry about that, but the picture is a little bit too busy for the right graph. Like, I don't know, how many? 9 vertices in the middle. Too many. So that's my vertex. Okay, and now what I'm trying to do, I'm trying to count homomorphisms from some graph or some digraph to this one. Well, obviously, the digraph I'm mapping should be also kind of on 3 levels, right? So it has to be balanced, obviously. Otherwise, there is no homomorphism. Also, I can do some pre-processing and so well. I mean, if you reflect a little bit, what kind of, if I want to find homomorphisms from something to here, what can I do to the input graph. That's pretty straightforward if you just try to think how things work. So I will take something very simple, like this, right? So it's P levels and so on and so forth. Right? Now, how do I define homomorphisms from there to my graph in a nice way? Well, obviously, if I tell how the bottom vertices are mapped and how the top vertices are mapped, then I have no room for no freedom for the middle ones, right? They have to be mapped somewhere, well, except for, well, those cases, like say if I map this guy and this guy to here and here, well, yeah, then that intermediate vertex can be mapped in one of the two, but nowhere else. It cannot be mapped here. So in some sense, what I have is, if, for instance, if I map A to 1, alpha to 3, then the number of options I have for the middle vertex is exactly this, and it is the entry in the matrix. So this is how the matrix corresponds to the number of homomorphisms. So the only thing I need is to decide how I'm mapping the top and the bottom. Okay. So then, how do I count the homomorphisms? Well, in a very simple way. I just sum up overall possible mappings of the top layer, all possible mappings of the lower layer, the number of degrees of freedom for the intermediate ones. So for instance, the first entry A phi of A psi of alpha would be for this two, right? Where I'm mapping this guy. The second one, A phi of A psi of beta, would be for this two, well, where I map this guy, and so on. So right now, generally it's an exponential along sum. I cannot do anything. It's impossible to compute. So the idea will be, I'm going to use the properties of the matrix that it has rank 1 to simplify the expression and really simplify. Okay. So since our matrix has rank 1, I can represent it as a product of two, I need a column by a row, right? So two vectors, anyway. I'm not going to draw them as rows or columns, so that will do. So if this is the case, then I can rewrite my expression as this. For A, phi of A psi of alpha, I will write B, phi of A C psi of alpha, and so on and so forth. So clearly the advantage of that is that now those things for phi and those numbers for psi are sort of disentangled. I can manage them separately. Now, what is the observation? The observation is that, this expression, if I focus only on phi of A, on this one, right? It appears a couple of times. But nothing else depends on this value, phi of A. This means that I can group things together and just sum up over all possible values of phi of A. You can say, okay, suppose phi of A is what is the, yes, phi of A is 1, right here. Okay, well, I have two occurrences of B phi of A, so it would be B1 squared. Phi of A is 1 here, right? The rest is like that. Then I say, okay, suppose phi of A is 2, right? Then I can do that, and well, the rest is the same. So that's the key. The rest is the same. Okay. So let's do it here. Well, that's our nice picture, the rank, and that's the computation we've done so far. Okay, group them together. Now the trick is clear, right? Well, I have to do the same with B, with phi of B. Nothing prevents me from doing the same thing with phi of B. Okay, now I get rid of phi completely, and I of course can do the same thing with psi. So that's my expression. Instead of exponential alone expression, huge sum and so on, well, I have a product. So what are the parameters of this product? Well, the summation in every term here would be just the number of elements in my set at most. Right, it's the number of vertices in the top or the bottom of that graph. So it's a constant number. It's a constant number. Well, here I would have some degrees or whatever. right? And the number of those factors, well, it would be one factor for every vertex on the top and at the top and at the bottom. So it's like just the number of vertices. Well, that's easy to compute. So that's the connection between the rank of the matrices and computing homomorphism. Okay, so that's the idea. Now, how do we make the same things, the same matrices in a more general case? For relational structures, when we don't have just such a nice three-level digraph or anything like this, what do we do in that case? Well, in that case, we are going to talk about equivalence relations. Because remember what we had in the picture of that diagram. Well, we had some vertices that were connected to the same vertex on the top, right? So they would have the same out neighbor, and vertices that would have the same again the same out neighbor. We had vertices that would have same in neighbor and so on. So if I just try to in that graph, both of those relations happen to be equivalence relations. Every vertex in the middle had only one out neighbor and only one in neighbor. So in that case, it would be just an equivalence relation. So let's talk about equivalence relations. Suppose we have two equivalence relations now on the same set, like vertices, for instance. Then I will use those relations to construct a matrix again. What will I do? I will take alpha classes. So classes of the first equivalence relation, right? In my small example, that would correspond to elements on the top. Yeah, okay. And the columns I will index using the classes of the second relation, so CJs. In the example, that would correspond to the elements at the bottom. The entries is just the intersection of these two classes. So I fix a class on the top, I fix a class on the bottom. How many vertices are in between them? That's precisely that. So that's more or less the generalization of the matrix we have for that small graph. Well, I will say that my matrix is block rank 1. If I can represent it as follows. So if I permute columns, rows, and so on and so forth, well, I can make the sorry, I can make those elements kind of in the blocks on the diagonal. Everything else is 0, and blocks on the diagonal all have rank 1. Well, this may happen. Unfortunately, well, if I'm going to look at arbitrary relations, I may have several blocks, unlike the small example when I had only one. So here I can have multiple blocks. Okay, block rank 1. So the good news is, if I have something like this, then I can solve, well, block rank 1. Then I can solve the count in CSP. So that's another reason why a count in CSP can be easy. If I take two relations, two equivalence relations on some set, and matrix is block 1, then this problem is easy. If it's not block rank 1, then the problem is hard. So that's another reason for hardness, another reason for easiness of my problem. So that turns out to be really, really foundational result. Well, all subsequent results uses it in big way somehow. So that's one of the central things. Okay, so we've talked about the rank, and one of the main things is now introduced. So the next thing, let's talk about. Okay, we have this equivalence relations, right? But we have a relational structure like a graph. Where do we get equivalence relations? Unclear. Generally speaking, it's not clear, right? Say in that little graph with 3 layers, okay, it was clear. We could do something with the middle layer and so on and so forth. But if you take a general diagram, equivalence relations, what equivalence relations? It's sort of not clear how we can get equivalence relations and use all these properties like block rank 1 and stuff like that. So to get those equivalence relations, we need this primitive positive definitions. So what is a primitive positive definition? I don't want to kind of spend much time on defining this thing. So again, I give a formal definition, and and give a couple of examples, very simple ones. Again, from that three-layered graph. Well, just to illustrate what it is. Well, we don't need to understand too much about it. Okay, so we think of relations as predicates, right? Okay, they depend on some variables and so on. So I say that a relation is primitive positive definable if I can express as a predicate, right? As I can express it through relations of my relational structures, well, equality doesn't matter, conjunctions and existential quantifiers. So if my relation R is, predicate R is, there exists some y1, y2, and so on, such that some conjunction of predicates from H is true. So let's look at a simple example. This is our three-layer graph, a little bit kind of deformed. So what I'm going to do, let's look at those vertices in the middle that have the same out neighbor, right? So these three have the same out neighbor, and these two have the same out neighbor. Well, I claim that this relation, which is equivalence relation here, can be primitive positive defined in the graph. So just using the relation in the graph, the edge relation of the graph. So let's see. Well, the formula basically states that I include two vertices in my relation if and only if they have a common out neighbor. This is what it says, right? There is a vertex such that X is connected to Z and Y is connected to Z. So these two guys will get into the relation, these two guys will get into the relation, but these two will not, because they don't have the same out neighbor. So that's exactly the idea. Well, clearly, in more complicated cases, I may have a very complicated formula here, but it doesn't matter. It's the same idea. So I can use conjunction, I can use predicates of my structure and existential quantifiers. Okay, now example, I also had another equivalence relation that worked like this. Right, so this is a, well, I include all pairs of vertices that have the same in neighbor. Right? There is a Z such that Z is connected to X and Z is connected to Y. So in this case, these two guys have the same in neighbor. These three have the same in neighbor, but these two do not. Okay? So that's basically the idea. Now, if I look at the matrix we constructed for this graph, 2, 1, 1, 1, it's exactly that matrix Fm of alpha beta. Exactly that one. So I take equivalence classes and so on, and put in the matrix the number of elements in the intersection. So that's the whole idea. Okay, so if I can PP define an equivalence relation in my structure, I will say that this equivalence relation is a congruence of H. Well, congruence came from universal algebra, actually, not from model theory. That's where these PP definitions belong to. But that's just terminology I'm going to use to avoid these PP definitions and stuff like that. Okay. So the good thing about PP definitions, why we need them, is this. If I have two structures such that every relation in the second one, in G, is PP definable in H, so I can PP define a structure in H, then it gives rise to a reduction between the corresponding count in CSP. So CSP of G is reducible to CSP of H. In that sense, if I can PP define something, I can use it to prove hardness. So for instance, in the previous slide, since I can define these two guys, I can immediately say, okay, well, this CSP is hard because, well, I know that for these two equivalence relations, the problem is hard. So that's what it's enough to just PP define bad relations, and we are done in a sense. Okay, and there is a lot of tools that allow us to play with PP definable relations and check which relations are PP definable, which are not, and so on and so on. So that's a big area. That is a big area. And one of the tools, I mentioned it here because it's kind of, well, it didn't play such a huge role in counting CSP, but for decision CSP, it was very absolutely necessary. But here it also kind of allows to simplify several things. So I will say that a relation, right, is invariant with respect to some operation. Right? So operation, n array operation means that it maps, say, h to the power of n to h. Right? It takes n arguments and outputs 1. If whenever I take several tuples from R, apply my operation component-wise, I get again a tuple from R. Well, I will give a couple of examples, and hopefully it will be clear how it works. So the set of all polymorphisms, well, in the standard way is denoted by polymorphisms of H. Okay, so what is good? Well, first of all, it's known that PP definitions is basically the same as are completely controlled by polymorphisms. So that was proved, like, well, I'm aware of 4 proofs of that fact. So one of them is mine, but I was kind of late for this thing. So it was my first work as a 4th year student, I guess. So I proved this nice thing. I thought, oh, it's very nice. I submitted it to a conference. They didn't say it's known. They said, come. So I came. Okay, come here. So I said, you know what? Well, what he proved is proved here, and it was just before you were born. So, well, this is another proof that, well, you probably wore diapers when that was proved. Well, now there is another one, and now there is yours. So that is really, really well-established fact, multiple times. So at least one of the proofs should be correct. Okay, how does it help? How it helps is this. Well, in order to understand the complexity of our problems, we just need to look at polymorphisms. So sometimes the properties of polymorphisms are more understandable and more and easier to use. And well, and still, that's the only thing you need to know about, well, to determine the complexity. So a couple of examples. Let's look at this binary relation. It's binary, so we know it's a digraph. Well, actually, it's a graph, right? Since it's symmetric. I claim that operations on 0, 1, which is max, just takes the maximum of the 2 inputs, is a polymorphism, and the operation min, which is the minimum of 2 inputs, is not a polymorphism. Why is that? Well, for max, for instance, what I need to do, I need to take all possible pairs of those pairs here, say 0, 1, and 1, 0, 0, 1, 1, 0. Apply max like this. Of course, max of 0, 1 is going to be 1, well, max of 1, 0 is going to be 1, and it's here. Everything's fine. Okay. For min, it doesn't work. If I take the same tuples, 0, 1, 1, 0, I take the min, it's 0, I take the min, it's 0, it's not there. So this is not a polymorphism, and this is a polymorphism. Fantastic. Another example, the one which that is useful for counting, actually. So let's suppose a relation is defined as a set of solutions of some system theory equation. So suppose that's the system that gives us that relation R. So R consists of all solutions, of all x's that satisfy the equation. Okay. I claim that this operation, so-called affine operation, x minus y plus z, is a polymorphism of that relation. Let's check. We don't need to substitute. We don't need to substitute any tuples because, well, that's linear algebra, right? So what do I need to do? I need to take 3 tuples from R, apply. Well, this means that if I substitute that in the system, I get a solution, right? So this equation, and I need to combine them using this function, and check that the result is again a solution of the system. So I need to do something like this. I need to combine them component-wise, okay? Multiply by the matrix and check if I get B in the end or not. But that's trivial, right? If well, multiplication here is linear, so that's it, right? Pretty easy. So the interesting thing is that such an operation is a polymorphism if and only if a relation can be represented this way. So this basically defines when your relation is affine. Again, if you know linear algebra, well, you easily understand why this is so. That's not a big deal. Okay. So again, go back to H coloring for a quick visit. So the operation from the previous slide is one of the special cases of so-called Maltsev operations. Maltsev operation satisfies, well, it's any ternary operation that satisfies the equations. Well, if I apply it to so that the first two arguments are equal and or the last two arguments are equal, I always get the remaining argument. So if you think about it, x minus y plus z, if x and y are equal, they cancel, I get the remaining one. If y and z are equal, well, they cancel, I always get the first one. Right? So this is a Maltsev operation. What is good about Maltsev operation is that it's absolutely necessary to have an efficiently solvable counting CSP. If you don't have a Maltsev polymorphism of your relational structures, it's hard. Well, that's actually something that that can be proved through well, fairly advanced results in algebra. So that's a kind of good quality result in the sense that it uses some tools from a totally different discipline and so on and so forth. So well, that's a good one. Okay, so I claim that if my graph contains a subgraph like this M, then it has no Maltsev polymorphism. Well, obviously it doesn't, right? If I apply my Maltsev operation, well, any Maltsev operation like this to AC, AD, and BD, right? Since it's Maltsev, I have to have B here, and I have to have C here, but it's not in the graph. Right? Okay, now let's use that to obtain that classification for graph homomorphism. So suppose I have this graph H. Suppose I have that graph H. Okay, we have two cases. It may be bipartite or it may be not. If it is bipartite, for instance, and it's not complete, I definitely have something like this. Right? So if my bipartite graph is not complete, well, one of the edges is missing, and that's it. Right? So I immediately have the structure. And we are done. It cannot be easy. So suppose it's non-bipartite. Suppose it's not non-bipartite. What can I have? What can I have? Assuming that my graph has a Maltsev polymorphism. Well, it means that if I have a three path, right, like that, I have to have this edge as well. If I have a Maltsev polymorphism, a three path means that I have to have this edge as well. Okay, good. So what does it mean? What does it mean? This means that 1, 2, 3, 4 somehow. Right. This means that if I start with my odd cycle in the non-bipartite graph, by applying this simple argument, I know that there is a triangle in the graph. If I have a 5 cycle, I can cut it a little bit and get a triangle. Okay, good. Now again, let's apply this logic there. So suppose this is C, this is A, this is D, and this is B. Right? I need to have this. So there is a loop in my graph. Okay, suppose I have a loop in my graph. Suppose I have a loop in my graph and I have something else. So I have something else. Then what do I need to do? I need to say this is C, this is A, this is D, and this is B. Well, I have to have a loop here. That's it, right? So it has to be a complete graph with all loops. Well, then it's complete now, kind of similar kind of argument. So, well, with all this machinery, proving something for graphs, it is totally easy. Okay, so now, well, we are close to that to the final result, actually. It's a couple of slides probably. Say, I want to define one more thing. How do I get congruences now? So, or rather, what congruences I use. So, projection congruence. Suppose I have a relation. Suppose it's 10. Well, why not? 3 is a good number. So let me define two equivalence relations here. Well, and they have to be equivalence because, okay, suppose that I have a relation that has a multiple polymorphism. Okay, so I can define two relations, and I can prove using that multiple polymorphism that they must be equivalence relations. So the first of them is a first projection congruence. That is defined as follows: two triples, well, two elements in the relation are in alpha if and only if x equals to, well, the first components. Right? The second one, the same for the second component. Now, what I want to do, I will construct a matrix that corresponds to those alpha and beta. Say, for instance, for this one, well, every entry, for instance, here it would be AA, right? Will correspond to how many extensions of AA I have. So for AA, I have only one extension, right? AA never occurs again, I guess. So this is one. That would be AB. For AB, I have two extensions, right? And AB never occurs again, and so on and so forth. So the corresponding matrix will be like that. These are the congruences I'm interested in, and these are matrices I'm interested in. That's all. I don't want to know anything else. Well, obviously, well, in principle, I may have, so I'm cheating a little bit here. I may have relations that are kind of longer, not ternary, but many coordinates. In this case, I won't say that I take just one projection, one coordinate here, one coordinate there. I would say, okay, take a bunch of coordinates, equate them, take a bunch of coordinates, equate them, and count. But that's what the idea is basically this. Okay, and now we can well state the result. So we call a structure singular if for any relation that is PP definable in that structure, and for its projection congruences alpha beta, the matrix is block rank 1. So that's singularity. This is singularity, and that's exactly when the CSP is solvable into normal time. So somehow the complexity of the problem is determined by ranks of matrices that are constructed in a pair. Okay, so a few comments on whatever remains of this problem. So I can look at weighted structures. Like for instance, for graphs, I can have unweighted graphs. I can put weights on edges of the graph. I can do the same thing for structures, and this basically means that I replace the predicates in my structure with just functions that may have natural values, integer, I don't know, whatever, up to complex values. Well, you can go further even than that. Okay, so then an instance of such a problem is going to be a structure, and the goal is to compute some value, which is defined as follows. For every mapping from G to H, I will define its weight as follows. I will take all predicate symbols. So in the case of graphs, just this means for every edge. For every edge, I will look at the image of this edge in my structure H and take its weight, and multiply all of it. So for every edge in my graph, I will look at the image, take its weight, and multiply all these weights. Something like that. So the goal is to find the sum of all such things. Now, if my relation is just regular, if my relational structure is just regular structure, not without weights, this R is a predicate, it's 0, 1. Every time it's a homomorphism, it has weight 1, and therefore this thing just counts the number of homomorphisms. Well, if it's something more complicated, I'm counting something more complicated. This is called partition function in this case. Okay, so what we know about that? For all these weighted CSPs, we also have dichotomies, and well, I mentioned some of them. It's not a complete list. It's been a kind of some process. So for positive rational numbers, well, the dichotomy can be derived fairly easily from the unweighted case. You just simulate rational weights using the numbers of elements, things like that. For rational numbers, things are a little bit more complicated because it turns out that if you take some function with weights like 1, 1, 1 minus 1, it's an easy problem, although the rank is 2. Right? So the problem is here is that if I take any orthogonal matrix, it will correspond to an easy problem. So that was a little bit more complicated, but people overcame that. Finally, for positive real numbers, it was done, and the last monumental result is about complex weights. So for arbitrary complex weights, the dichotomy is also known. I won't even mention conditions here. So they're kind of based on those block rank 1 conditions, but it's way more complicated. So there are many things that can go wrong here. And that's it. Thank you. Yeah.
Oh, so for the weight you just talked about, you know why the people keep checking the real numbers and the positive complex numbers?
Say it again?
Like the R and the C class, why don't we have results on those?
Just about R.
Yeah.
So well, they got for positive reals and they kind of figured out how to do it for complex. I mean, well, if you have a result for complex numbers, it gives you the result for reals, no problem. It's more general, right?